Welcome to AP Calculus, you're gonna know it all by the end of this. All the basics, I'm giving you the basis. You'll be loving math when the rap's terminated. We're gonna learn a lot today. Derivative, integral, related rates, antiderivative, and the FTCs. Now pick up your pencil, start writing. Take the derivative, slope of the tangent line of a graph. Tangent means that there's only one point the local line borders at. If we know what the slope is at every point of the function, then we can find how it changes in its domain. But how do we even do it? First, what's the slope? 2 points on a graph. Draw a line in between them, it's as simple as that. A line that crosses 2 points on a graph is a secant, and like any other line, find the slope between the points with difference of the y over difference of the x, with tangents only got 1 point, so here's what happens next. The difference of the x we'll call h and replace the slope equation for this case. Now we've got f of x plus h minus f of x over x plus h minus x. X cancels out, so the h is left, so the limit h is 0, so the points will overlap and we're done. Derivative definition, now we can know the slope at any point that we want. The derivative is a function, meaning it can be reversed with the antiderivative. Take a look at how it works. The notation's an s stretch to look like a slide. That's an indefinite integral, much harder to find. Add a dx in front of the function. Now you know the function, the integrand, no assumption. When you integrate, you better not forget the plus c. That's a constant that makes the function ambiguous vertically. When you differentiate, the y values are lost without an initial condition. C is all you've got. Now how about a new concept? Take the space between the function and the x-axis. If we want to find the area on an interval, it's strange because the space inside is not a shape we easily calculate, but approximate it with rectangles. As the width gets smaller, the area gets close. If we add up the areas as the width goes to 0, then on the interval a to b we'll have the answer we need. So the width of 1 is the interval divided by the number. The height of 1 is simply just a function. B minus a runs the width. The height is more intricate because the height at a point is the function evaluated at a single rectangle position. If the function is f of x, inside put the width we calculated, multiply by I, that's a rectangle's position at a, so the points inside the interval we're in. It's a summation equation, we're rocking same notation. We have to multiply the width and height, then add every position starting at position 1. The rectangle goes to infinity. Take the limit, now we have every piece that we need. Sigma I goes 1 to n, limit n goes to infinity. A b minus a over n times f of b minus a over n times I plus a. Wash your v's away, Riemann sum is here to stay. As a definite integral is easy to say. Integral of a to b of f of x dx. It's as simple as that, no need to double check. Now we've got both roots of calculus, but how do we connect them? Switch it. We've got both derivative and integral in front of us, linked by the fundamental theorems of calculus. Call them FTC1 and FTC2. If you can't remember these, then you never get through. Overall, both theorems are the same message. Derivative and integral are inverse functions. Opposites, yeah, they reverse each other. You get back the same function putting ones on the other. Now before we start, here's a quick remark for integration. Indefinite, indefinite, completely different statements. Indefinite is the antiderivative, it's a function. Definite is an area, it returns a constant. Now that we have that out of the way, I think it's finally time to explain both FTCs. It won't take long. Let's start with the first one. Okay, starting easy, integral a to b of the derivative of f of x dx equals f of b minus f of a, that's all. Input the interval in the definite integral, we're done. Now we're on FTC2, though before we proceed, I've got to warn you, there's a lot to take in, and I'm not going slow. 3, 2, 1, go. Imagine a definite integral with a modification. Take the second bat away and put it in exercise. Place whatever x was in the integral and replace it with the t and change the x to match it so the integrals in harmony will be created as a function of accumulation as the x increases area underneath the graph. Change the second FTC states that if we take the derivative, then the output is the integrand, the function we're dealing with, that's it. This also shows the accumulation is the same as the indefinite integral. That's critical. Two sides of the same coin, definite, indefinite, not completely unjoined. Now you know the basics of calculus. Every theorem evolved from it. You better thank Newton and Leibniz for all their contributions. I've got one final lesson. You made this far, and I know you've got it. We don't have long, but we'll be fine. Ready? Switch it up one more time. Taking it slow as the volumes get high. Areas change, now we're dealing with time. Gradually growing, infinity flowing. Though it's staying pure math, but we're now applied. If you've taken geometry, then you know what's coming next. Find the volume equation of the container you're filling, or the area expanding. If it changes, differentiate it, but there's no time, so we got a chain rule. Real quick, gotta explain this chain rule to the derivative of a function. In a function to do this, gotta derive the function on the outside, plug in the inside function, then multiply the whole thing by the derivative of the inside. Got that down, you'll be doing just fine. Now let's get back on time out. Whatever equation you're manipulating, doesn't matter if it's length, area, or volume. All I'm saying is you gotta DDT and differentiate by time, then chain rule the variables you find inside. Cause if you know the rate of variable changes, then do some algebra to find the unknowns in the equation. They get difficult as more different variables show up. You'll either need more information or they're related to each other. Now it's possible to get a volume from a function. Of course, you'll need an integral, but that's not all of it. There's a lot to explain, but we've only got a minute, so hold on to your pencil, I'll explain it real quick. Kick it. If you treat the values of the function like a radius, you're able to create a disk, zero width, file them together all in the function, and the result is a weird solid. The volume is the sum of all the disks. Each one is the circle's area times the width, pi r squared, but r is the function, and the sum of all the widths is the integral of it. So pi integral it'll be of f of x, and the grand squared dx. What's next? Switch it to accumulation. Now it's the volume as the high changes, ddt, and chain rule, that's the way. Now you know related rates. Thank you for your time, yeah. I hope you learned today.